Yeah, so we are looking at Marchenko-Pastur law. We want to understand the asymptotic eigenvalue distribution of Wishart random matrices. And we already saw that we have concentration, which means that the eigenvalues of those matrices are very close to the average behavior, or that they are always very close to the position. Okay, so it's enough to understand what is the averaged eigenvalue distribution of those matrices, and that's what is given by this Marchenko-Pastur law. So I just recall. So that's what we want to prove. So this was Marchenko-Pastur who proved this. So our setting was, we are looking on our Wishart, on our matrices, okay, which are coming from our data matrices. So X is a matrix P times N, so it consists of N independent draws of our datas. So P is the dimension of our datas. So this should be a standard Gaussian random matrix. Standard Gaussian random matrix. So with this I mean that all the entries of X are independent and they have all the same distribution, namely they all have a Gauss with mean 0 and variance 1. Okay, and then we want to understand this in a very specific regime, so namely not fix P and let N go to infinity, but at a regime where P and N both are large, of the same size. So we look on the asymptotic situation where, I mean, they both go to infinity, but their ratio goes to a constant, and then the result will depend on this constant. So that's what I called gamma. So we assume that P divided by N goes to gamma in the limit, where gamma, I mean, here I restrict to the interval between 0 and 1, but the same is more or less also true on the other side, but then I have an additional atom. So in the form I put it here, it's for this regime, but I can of course also extend it to the other side. Okay, so if N goes to infinity, and this means also P goes to infinity, like gamma N, then we say that the histograms of the eigenvalues of the corresponding Wishart matrix, so the statement was the histogram of the eigenvalues of, okay, not of X, because X is a rectangular matrix, this doesn't have eigenvalues, but of the corresponding Wishart matrix, which are denoted by sigma hat, and this was by definition 1 over n X times X transpose. So this is a symmetric P by P matrix, so this has real eigenvalues, and we can look on the histograms, and we say this converges to very specific distribution, which we call Marchenko-Pastur density. So this is psi MP of T. So this is a probability density, which depends, of course, on gamma. And so the explicit form is 1 over 2 pi gamma T. And then I have here gamma plus minus T times T minus gamma minus, the square root of this, where this gamma plus and gamma minus are calculated from gamma. And this here lives on the interval where the square root is a square root of a positive guy, which means T has to be between gamma minus and gamma plus. Gamma minus is the smaller one. And so this lives on gamma minus up to gamma plus, this interval, and gamma, let me say plus minus, this is just 1 plus or minus square root of gamma, and the whole thing squared. Okay, so that's the statement, and I mean we checked in the assignments that this really seems to be the case. I mean, we looked on the histograms of those matrices and we compared it to this, and this is really a very good fit. Okay, but we want to prove this, to understand this, and yeah, how do we prove such a thing? So I already said last time, I mean, what we are claiming here essentially that the histograms are converging to this law means essentially that we have a convergence of specific averaged functions of the eigenvalues. Okay, and so maybe let me write again. So what we actually what this says is that, let's say 1 over P, the sum over 1 from 1 to p of f of the ith eigenvalue. So lambda I up to lambda p are the eigenvalues of my Wishart matrix. We are claiming that this converges in the regime we are considering to the corresponding integral with respect of this function with respect to the Marchenko-Pastur density. Okay, and for the histograms, I mean this f which I'm taking here are characteristic functions of, let's say, interval a to b. So a function which is 1 on this interval and outside if it is not. So for with this function, I'm here just counting whether the eigenvalues are in this interval or not. That's what my histogram is telling me, how many eigenvalues are sitting in. Okay, I mean, the histogram gives me the bins, but of course then I can sum over some bins, and then I know how many eigenvalues relative are in this interval. And this corresponds to the corresponding area under the Marchenko-Pastur law. So that's what we are saying here. And yeah, now I already said last time, I mean, to prove it in this form for functions, I mean here, so the histograms, this means I'm looking on functions where f of lambda is a characteristic function of an interval ab of lambda. And to prove this in this form is not so clear how we should do this, because we don't really have good control of the eigenvalues. We don't have concrete formulas. Okay, so the main idea is that we prove this for other functions. So namely, we consider instead functions either we are looking on moments, which means we are looking on powers of n, or what we are going to do is we are looking on resolvents, which means f of lambda is 1 divided by lambda minus z for some complex numbers. So this here depends essentially on n, and this here depends on z. So it's a collection of functions, and we are going to prove this. And why should we do this, or why should this be easier? The point is that, okay, the eigenvalues we don't have direct access to. If I'm summing here over the eigenvalues, I mean, this is essentially like taking a trace. So this is going back to the matrix itself. Instead of the eigenvalues, we should go back to the matrix and its entries where we know really how they behave. Okay, I have here the sum over a function of the eigenvalues. This is like the trace of the function of the matrix. Okay, I mean, taking the trace of a matrix means I'm summing over the eigenvalues, and the trace of a matrix is something which is given in terms of the matrix entries. Okay, but we have this function, and the characteristic function of the matrix, this is not clear how we should deal with this, apart from going back to the eigenvalues. But if we take those other functions here, then this is something which we really can write down as a genuine function of the matrix. I mean, here we take just a to the n, and here we just take this function of the matrix. And this means we really go back to the matrix. We take the trace of something in the matrix, and then hopefully we can understand this in terms of the entries of the matrix. Because the entries of the matrix, this is something where we have good control. The eigenvalues we don't really know so much. It's hard to control them directly. Okay, so that's the reason why instead of proving this, where we don't really know what we should do, we prove either this or this, and then both of them in this situation is equivalent to this here. So this follows from general machinery, which I'm not going to go into, but essentially, that is well known. Okay, so I want to prove it for this function, and then furthermore, we also know, because of concentration, it's enough to prove the whole thing for the expected value. So instead of taking here the function of my eigenvalues for given the realization, I can do this for the expected value. So maybe I can put the expected value here. So that this converges. This is good enough, because we know already that for each realization, I'm very close to the expected value. So if I know what happens with the expected value, I also know what happens in typical realizations. Okay. Yeah, and of course, I mean, this is deterministic. This is always the same result. Okay, so that's what we want to prove. Yeah, and maybe the first thing which I'm going to do is now really making this transition from this function in the eigenvalues for this function to something which is given in terms of the trace. I mean, this is very easy trivial, but maybe let me do it explicitly. So because that's what we are going to use. And I mean, this is a general statement, of course, about matrices, that if I have a trace of a function of a matrix, this is the same as taking the averaged sum of the corresponding function in the eigenvalues for self-adjoint matrices. And let me do this for this function here. Okay, so for this, let me consider matrix A, which is a P times P matrix. So A will later be our Wishart matrix. And yeah, so let me assume this is symmetric. A symmetric matrix. So this means it's equal to its transpose. Okay, and then of course we know that such a matrix has with multiplicity P eigenvalues, and they are real. Okay, so that's what we know from linear algebra. So this has eigenvalues, and we know they are real. And there are sufficiently many, if I count them with multiplicity. So I'm writing down the characteristic equation, and this has P solutions. And I denote them by lambda 1 up to lambda P. Okay, and then I'm claiming that if I'm looking on this quantity for this function, that this is the same as a corresponding function, the trace of the corresponding function of my matrix. So then, okay, here my function depends on this parameter set. So we have this for each set. But of course, I mean, if I take this function, if set is equal to lambda, it's problematic, so I should avoid this. But I know the lambdas are the eigenvalues, so if set is not real, then I'm sure that this never gives a problem. That's the reason why I'm not taking set on the real axis, but I go to the complex plane, and let's say usually I just consider the upper half plane. I could also consider the lower one. I should avoid the real axis, because I don't know where the eigenvalues are, so I don't know. I'm not so sure what I should avoid, so better avoid the whole real axis. Then it's always okay. So for any set in C, or maybe here I'm just saying, okay, maybe just avoid the eigenvalues, because I have here the eigenvalues. I have names for them, so I can say I avoid all of them. But later, if we talk about collections of matrices, I just avoid the whole real axis. But let's say here, just for this statement, if I take sets which are different from the eigenvalues for all 1 up to P, then we have that this quantity in which I'm interested, so I'm summing from 1 up to P. Yeah, and I'm averaging, so I'm dividing also by 1 over P, and I take the function 1, and then I take lambda I minus z. So for my function here, I'm just taking now this function here. So for z is fixed, so this is a function of the eigenvalues. This I'm claiming is the same as the trace of my matrix A, and so I take the same. I replace just the lambda by the A. So I take A minus z inverse. And of course, subtracting z means I'm subtracting, if I'm now in the matrices, I'm subtracting the identity matrix. So z minus the identity matrix in P dimensions. I take the inverse of this, and then I'm taking the trace. So this here is this function here, and the trace corresponds to this averaged sum. And I'm averaging here, so this trace, which I denote here with this little t, is a normalized trace. So where little tr is the normalized trace by 1 over P of the usual trace. The usual trace of a matrix is just summing over the diagonal, but I'm normalizing this by P because I also have here the normalization. So this is the normalized trace on P by P matrices. Good. Okay, the proof of this, I mean, maybe hopefully it should be more or less clear to everybody, but let me nevertheless do it. So because this is of course important ingredient of what we are doing here. So this is just basic linear algebra stuff on diagonalizing matrices. Okay, so we have a symmetric matrix, and of course we know that we can diagonalize this by orthogonal matrix. Yeah? And in a diagonal form, we just get the eigenvalues on the diagonal. So that's the maybe one of the basic statements about spectral theory of matrices. If I have an orthogonal matrix, no, a symmetric matrix, then it can be diagonalized by an orthogonal matrix. And I mean, the orthogonal matrix contains the eigenvectors of my matrix. It can be diagonalized by an orthogonal matrix. So the fact that this is orthogonal just means that the eigenvectors, the different eigenvectors, are all orthogonal to each other. I mean, that's the two main statements about symmetric matrices. The eigenvalues are real and the eigenvectors are all orthogonal. Okay, to each other. So I put them into an orthogonal matrix. Maybe I call it O. And orthogonal means, of course, then that O times O transpose is the identity matrix, and of course also the other way around. Okay. Yeah. So this means the columns, the columns are all normalized to length 1, and they are all orthogonal to each other. And here for the rows. Okay, and this diagonalization, of course, is in the form so that I can write A as O D O transpose. So I'm making a change of my basis. I'm going to the basis which consists of the eigenvectors of my matrix. And then in this form, the A gets transformed into D, which is a diagonal matrix. And this diagonal matrix just has the eigenvalues on the diagonal. So D is a diagonal P by P matrix, where I have lambda 1, lambda 2, up to lambda P on the diagonal, and 0 everywhere else. Good, okay, but then, okay, I can now look on this side, and now of course I can calculate this side in this form here. So now I can, of course, consider, well, what is this? So here I want A minus Z times the identity matrix. Okay, so let me first write this in this form. So this is then, I say it's O D minus Z I P O transpose. I mean, A is O D O transpose, and the identity I also have written as O identity O transpose, which is of course the case because O transpose is the identity. Okay, so it doesn't do anything with the identity matrix. Yeah, and then of course I can now invert this. So A minus Z identity matrix to the minus 1. That's what I want there. Of course is now the inverse of this. Okay, I mean the inverse of a product is the product of the inverses, just in the other order. And the inverse of O and O transpose is of course just the other one. I mean the inverse of O is O transpose. I mean that's exactly what this here is saying. O transpose is the inverse of O. So I take the inverse of this, but it's moved over there, so I still have the O there. So this is O. And then I have to take the transpose of this, D minus Z identity to the minus 1. And I mean I have the inverse of this, but moved here. But the inverse of this is O transpose. So you see I have the same conjugation of the corresponding function in D. Yeah, and now so now of course I can apply, maybe now let me apply the trace to this guy. And then, of course, the effect of the trace is that the O disappears. That's the main thing. I mean, up to this point, if I just deal with the functions themselves, I mean, it's a function of the diagonal thing, but I still have to transform it back into the old basis. But if I take the trace, I don't care about this anymore, because the trace does not change under change of the basis. So let me take the trace of this then. I mean, that's the thing we are really interested, where we want to see that it is given in terms of the eigenvalues. So the trace of A minus Z times the identity matrix to the minus 1, trace of this So this is then, so this is 1 over p, like the ordinary trace of, yeah, and I mean we have seen this, I can write it as O, and then the inverse of the corresponding thing where I replace A by D, D minus Z times the identity matrix, minus 1 O transpose. Yeah, and now the main point is that the trace, I mean the trace has the property, the trace of AB is a trace of BA, which means I can move something from here to the end. So this is the same as this times O transpose times O, but O transpose times O is 1, so this disappears. Or it's just maybe even more basic fact that the trace is not changing under orthogonal transformations. So that's what this is saying, that this is the same as 1 over P, and then taking the trace where the O has disappeared of D minus Z IP minus 1. And I mean, this really shows that, D contains the eigenvalues, and now we are almost there. But this shows how going from something where the eigenvalues are there, going back to the matrix, this is achieved very nicely by taking the trace. Okay, and on this here, of course, this is now exactly what I have there, just because here this is a diagonal matrix where the eigenvalues are on the diagonal, and of this I can of course take the inverse. So I mean we have of course now that D minus Z times identity. So what is this? Yeah, this is, or let me okay, so this is just the matrix D, and then I'm subtracting Z times the identity. Z times the identity is just a matrix which has a set everywhere on the diagonal. So I'm subtracting from lambda 1, I'm subtracting Z, from lambda 2 I'm subtracting Z, and so on. From lambda p I'm subtracting Z, and everywhere else I haven't done anything. Okay, and now I don't want this matrix, but I want the inverse of this. But taking the inverse of a diagonal matrix, this is easy. I mean, taking the inverse of a general matrix is not so easy, but a diagonal matrix, this is very easy, because I just take the inverse of each element on the diagonal. So I take here just the inverse of the first entry. I take the inverse of the 2 entry, and so on, up to the inverse here on the PP entry. And everywhere else, of course, nothing happens. Yeah, and now you see I have this matrix, and if I now take the trace of this is just the sum here, and I normalize it by P, and so the trace gives exactly what I have here. So this, this gives me the assertion. Because the trace of this is exactly this. So this is just, this is very general. This does not rely so much on a specific form of the function which I take here, but this is true for any kind of function for any polynomial or any rational function which I can write down as such a formula, where I can also write down a function of the matrix, because it's given in algebraic terms. Good, okay, so we see that for such functions where I have kind of explicit algebraic formulas, I can go over from the eigenvalues to the matrix. And that's good, because then I'm back to the matrix, and then I can calculate things in terms of the entries of the matrix, and there I have a good knowledge. Yeah, okay. And so of course what I have done here, if I have a specific matrix, I should avoid with Z the eigenvalues, so that my function makes sense. And if I now take matrices, and if I take my Wishart ensemble, I have many matrices, and they might have very different eigenvalues. So I don't know where they are sitting exactly. So I'm just avoiding all of the real axes. So in the following, Z will just be, let's say, in the upper half plane, avoiding R. And then all this is true for any matrix which we consider. Okay. And now, so we see what we really now should try to understand is this kind of function of our matrix, and see that this converge to the corresponding, to the integral over the corresponding function with respect to the Marchenko-Pastur density. Okay, and those quantities here, which I consider now as a function of Z. For each set I have this. These are very important quantities for matrices, and they have their own name, and they are called Stieltjes Transform. So what I'm doing here is really the Stieltjes Transform of my matrices, and I want to see that they converge to the Stieltjes Transform of the Marchenko-Pastur law. Yeah, okay, so let me just define those guys. Stieltjes Transform is just a name for those functions. So let me define the Stieltjes Transform of the matrices and the Stieltjes Transform of the limit. So, and our matrices are the Wishart matrices. So for our Wishart matrices, so those were of the form sigma hat 1 over n x transpose. We define what we call the Stieltjes transform. We define their, so Stieltjes was a famous mathematician, Stieltjes transform as, and I consider it as a function of this parameter set. So I write as yeah, and let me put an n here because yeah, I'm looking on a matrix where I have this n here. So I have a p times n matrix. So it also depends on p, but p, let's say, is gamma times n. So it depends on n. And so I write Sn, and then it also depends on this parameter set. And it is given by this trace of the inverse, but we also take the expected value, because we want to prove things for the expected value. So I take here the expected value of the trace, the normalized trace of my Wishart matrix, sigma hat, minus Z times the identity matrix, yeah, taking the inverse of this, and then the trace of this thing, and then the expectation of the whole thing. And let me do this for Z, which is a complex number but not R. Because I mean, if I average here, I average over all possible numbers, over all possible Wishart matrices, and the eigenvalues can be more or less anything. Of course, they are positive, so it would be enough to exclude the positive real axis, but anyhow, we don't care so much about this. Okay, so that's the Stieltjes transform of our Wishart matrices, and so we want to see that this converges in a limit, if n goes to infinity, to the corresponding quantity for the Marchenko-Pastur law. And there, of course, for the Marchenko-Pastur law, we should integrate over this function here. So for our Marchenko-Pastur law, we define the corresponding object. So for Marchenko-Pastur distribution, which was a density psi mp, which is given here in explicit form. We also define it Stieltjes transform. We define Stieltjes transform as the same kind of object. So let me call it SMP for Marchenko-Pastur. Again, it depends on Z, and it is given by integrating this function 1 divided by t minus Z with respect to my Marchenko-Pastur density. And again, I'm doing this in C minus R. But of course, in this case, I mean, if I'm outside of this interval, then it would be okay. But still, let us just exclude all of R. Doesn't make a difference. Yeah, okay. And so what we have to prove is that actually this guy here, for any set in the upper half plane, converges to this here. That's what we have to see. I mean, that's our idea. In principle, we would like to see that if I have here the characteristic function of my matrix, it converges to this. But the characteristic function I cannot really express in nice terms so that I can handle it. But we know this is the same as proving it for this kind of function, which I can express very nicely. And so we have to see this. Okay, so to prove, maybe. So what we have to prove is that for all set which are not in R, that we have that Sn of set converges in the regime which we consider, which is n going to infinity and p also going to infinity as a multiple of n, as a fraction of n, gamma times n. So in this regime, this should converge to the corresponding Stieltjes transform of Marchenko-Pastur. Good. Okay. And so the question is, how do we do this? I mean, now of course, okay. The main work is to prove this. And in this proof, one should also see why we get Marchenko-Pastur in the limit. I mean, we start somewhere here by our Wishart matrices, and we want to show they converge to something, and we should identify this something. And in this language here, of course, we have to identify the Stieltjes transform in the limit. So we need to get somehow a Stieltjes transform which tells us that we have this distribution. And the idea is that what we are going to derive is an equation in a limit. So we are trying to get equations here and then see what happens with those in the limit, so that we get an equation for the limit which then should have this solution. Okay, but so let us see how this will work. So the idea is we will derive an equation for the limit, and of course one also has to see that the limit exists of this here. I mean that's part of the proof. But this follows by maybe general theory if we have enough information. So we derive an equation for the limit in this regime here, where n goes to infinity, like this. And we will assume that the limit exists. So I don't want to talk too much why the limit exists. So there are additional arguments where we see that if we have equations, that we also know by compactness arguments that there must be a limit. Okay, okay. But I just want to look on the equation itself. So because that's the main information how we see what we get in the limit. Okay, so I will assume that the limit exists, and then of course we have to check that this guy here, what we get is the Stieltjes transform of the Marchenko-Pastur. Then we have to check that S of Z is actually Marchenko-Pastur Stieltjes transform. Good, but the main point, of course, is to get an equation. And so how should I get an equation for the Stieltjes transform? And the idea is, I mean, I have here the Stieltjes transform of a matrix, and this matrix is essentially given by adding up many data. So I mean, I have my p vectors, and I have n copies of them, and I'm summing them up. And now the idea is that I should say if I have n or one less data, it should be more or less the same. It shouldn't make a big difference if I have if n is big. If I have made n or if I have made n minus 1 observations. So if I leave out the last data vector, then I should have more or less the same Stieltjes transform. But on the other hand, I mean I see what I do something with my matrix, and I can try to check what this does. So I mean I'm leaving out one of the data points, which means I have more or less the same Stieltjes transform, but on the other hand, leaving out one guy means I'm doing some operation on my matrices, and I can maybe try to see that what this really means for the entries. And this gives me an equation. Okay, but this is okay. This is one really has to see it concretely. I mean, in this abstract way, it might sound reasonable, but of course one has to see that it works. And so maybe so let us note that what I have is, so I mean my matrix X is my data matrix where I'm putting in n independent copies of my vector from R to the P, which has this standard Gauss distribution. And my Sn of z, my Stieltjes transform, so this is the expectation of the normalized trace of what? Yeah, of 1 over n, the sigma hat. Sigma hat has a 1 over n. Maybe I'm taking out this 1 over n. Then I also multiply this with n. So I have here, let me write it like this, 1 over n. So the sigma hat is x transpose. But of course I can also write this as summing over those guys. So I have the sum from 1 up to n, and then I have xk transpose minus, and now I have taken out the n here. So I multiply here with n times z minus the identity to the minus 1. Yeah, trace and expectation. Yeah. Okay. So x transpose is the same as this. It's a sum over taking all the products of xk with xk transpose. And so what I have here is the sum of my data vectors, and I'm summing over n of them. And now I say, okay, instead of summing over n, I'm summing over n minus 1, and then I have an additional 1, and this additional 1 is a kind of perturbation what I had before. It's a small thing, and I should be able to make an expansion where I express the guy where I'm summing up to n in terms of the guy where I'm summing up to n minus 1 plus something which I should be able to control. And that's the idea. So maybe let me yeah, let me write it down there. So that's the idea how I want to compare the situation where I have n data points with the situation where I have n minus 1. Yeah, I mean I can also yeah, I can take this out, this 1 over n. It goes here with, let me see, 1 over n. I think the 1 over n is still under the minus sign. So maybe I should put it like this. So it gives an n, and I can take it out. And then the normalized trace is a 1 over p. So let me write it in terms of the unnormalized trace. So essentially, I mean, I have here, I can bring out the n, this n here. And this trace I can replace by the normal trace, and then I have here an n over p. And it's good to have this ratio because this goes to gamma. This is really a ratio which we would like to have because that's we can control asymptotically. Okay, so we have the trace here of this sum, and now I'm saying this sum here, this maybe I should see this as a sum where I only sum up from 1 up to n minus 1. Then I have yeah, xk transpose, and then I should add the last term, which is xn transpose. Yeah, and this guy here, this is a small deformation of this guy here. And I mean this here minus this is more or less the same as I had before, but I have a small deformation, and this is a rank 1 deformation. I mean this is a matrix. X is a vector, but I have a column vector times the row vector. This is a matrix. So this is a p by p matrix, but it's just a rank 1 matrix. So in a sense it's small. It's a small deformation of this one, and so we are taking here the inverse of a matrix which is deformed by a rank 1 guy, and the question is, can we write this in a form which is very useful? And actually this we can write this in a very nice form, and that is the next lemma which I want to give, which also has a name of itself. This is a Sherman-Morrison formula, but this is also a very nice statement about perturbations of taking the inverse of a matrix which is perturbed by rank 1. Okay, let me do that. I mean all this, I mean one really has to see the concrete formulas and then really to see that they are useful. And so let me do this following. So this is a statement which is independent of our actual frame. It's just about matrices, adding to a matrix, a rank 1 matrix, and then taking the inverse and check whether I have nice relations between them. So let us maybe first do this. So here's the lemma. So this usually goes under the name of Sherman-Morrison formula. But it's a very basic formula which shows up in many contexts. Good. Okay, so the setting is I have, let's say, a P by P matrix. I mean, this will be something like this. And then I have a rank 1 deformation, which is given by two vectors, let's say x and y. X and y will be in our context xk and x, or xn. Okay, but here they can be more general. So they are just two vectors. And then I'm looking at my matrix A, but I'm adding a rank 1 matrix to it coming from x and y, which is given by x, y transpose. So this is a P by P matrix. X is a vector. I think of it as a column vector. Y is a column vector, but y transpose is a row vector. So it's a column times a row, which is a matrix. Okay, so this is a matrix, a P by P matrix, but it's rank 1 because I can write it. It's the outer product or whatever of vectors. Okay, so I'm looking on this, and then I want to take the inverse of this. The question is, can I express this more or less in the inverse of A plus something? And this here tells me that this is an exact formula. It's a to the minus 1 minus a to the minus 1 x y t a to the minus 1 divided by 1 plus yt a minus 1 x. Yeah, okay. Whenever this makes sense. In particular, whenever, okay, a should of course be invertible, and I'm dividing by this. And maybe dividing by this, one should think about, I mean, what is this guy here? Is this a vector or is this a number? So here I take y transpose. So this y transpose is a row. Then I have here a matrix. And this here is now a column. And so if I multiply it like this, what is this? Matrix or number? Yeah, number. It's the inner product. I mean, this here gives a vector, and then it's the inner product. So if I multiply row with column, I get the inner product between the two vectors, which is a number. If I do it the other way around, like here, then I get a matrix. Okay, so this means this here is just a number, and this 1 here is really the real number 1. It's not the identity matrix. Because if this would be a matrix, I should add to it another matrix. Okay, so this is really, this here is a number, and then dividing by a number is also no problem. Dividing by a matrix, I mean, maybe I should see whether I write it on the left or the right side. But so this here is really just a number. And of course, I mean, this formula only makes sense if this here is different from 0. Okay, but so, I mean, this formula is true whenever it makes sense. So this means, of course, A should be invertible. And what I have here in the denominator should be different from 0. So whenever this, and 1 plus yt a to the minus 1 x is not 0. And when this is the case, then this guy is also invertible, and the inverse is given by this. That's a statement here. And maybe, yeah, let me write down, yeah, maybe note it here. So note x y transpose, as we have it here, is a matrix, is a P by P matrix, and it has rank 1, but it's a matrix. But if I do it the other way around, yt x, this is a 1 by 1 matrix, so it's really just a real number, and this is nothing else than inner product between x and y. Good. Okay. And in the same way, if I put something in between here, then it's the inner product. So I mean, if I have this here, so y transpose a to the minus 1 x, this of course is the inner product between y and a minus 1 applied to x. Like I have it here. So I mean, this here would be y transpose, this here would be y minus 1, and this here would be x. Applying this matrix to x and then taking the inner product with y. Okay, so just to be sure that, because it might be confusing, but it's nice to write it down. I mean, it's just matrix multiplication, but matrices of different sizes, and if I do it in one or the other order, it gives me something different. Okay, but the formulas make sense. Okay, so let me prove this. I mean, this is basic linear algebra, and in principle, you could just prove it by showing that what I have written down here is the inverse of this guy, by just multiplying and check it. But maybe let me do it in a way that we see where this formula comes from. And I mean, if I have an inverse of something, which is a sum of terms, usually the only way to get explicit formula is that I have a geometric series in the background. That I really have a geometric series, and then I can expand things, and then maybe I can massage them a bit and collect them again together and get the other side. That's what is going to happen here. So let me do this. Yeah, so let me start from the left-hand side and check what we can do. So I have A plus x y transpose. I want to take the inverse of this, and okay, I want to expand it as a geometric series. So of course I should write it as identity plus something, because that's a geometric, or minus something. That's where the geometric series gives me an expansion. And of course, I mean, if I have here an a which is invertible, I can put out the a to the minus 1, and then I'm left with the identity. So I'm writing this. I mean, I write this here as a times the identity plus something where I also divide the a to the minus 1. So, and the a I'm taking out, and I'm left with ip plus x yt a to the minus 1 to the minus 1. So I'm writing this as the identity plus this guy multiplied with a. The whole thing is multiplied with a, but then under the inverse this comes out. Or you can say I can multiply this here in as the inverse of the inverse as a from this side, and then I have exactly this here. So this is just putting out the a to the minus 1 so that I have here the identity. Okay, and then of course I can now use the geometric series. So this is the identity plus something. Of course, usually I should think about whether it converges or not. So this something should be smaller than 1, but I'm just doing it formally. So I mean, if things are small enough, it converges and it makes sense. And I mean, essentially I get this formula. If it does not converge formally, I mean, if it is true for small enough things, then it is true always. So because it's a linear algebraic equation. Okay, anyhow. So and in particular, I just want to see it formally. And then if I have the formula, I can just check that this is the inverse of the other side. And for this, I don't need a power series expansion. But so how do I get this side here? Yeah, I do this expansion. So I have I to the minus 1. And then, I mean, the geometric series tells me that I'm getting here the sum of the powers of the guy. And I have here a plus, not a minus, so I will get alternating signs. So I have the identity IP minus, and then the first term is x y transpose a to the minus 1. Okay, and then the next term is this guy squared, so it's x y transpose a to the minus 1, x y transpose a to the minus 1, and then so on with alternating signs, minus, plus, and so on, powers. Okay, and now we see that we get some simplifications, or we get here, if I multiply those things together, I get some interesting terms. Namely, what I have here is yt a minus 1 x. And this is a real number. This is the inner product between this and this. I mean, this is what we have in the denominator later. So you see that those guys appear here. So this here is a real number, and this I can commute with other things. Of course, I'm multiplying here matrices, so in general I cannot commute things, but if I see that some of the products are just real numbers, then I can move them out. So I mean, I can move this here out, and then you see what I'm left with is the x, y transpose a to the minus 1, which is exactly this term. So what I get here, if I also take this here into account, is I get always x, y, t, a to the minus 1. This remains, but then the other things are multiplying together to real numbers, which are just, I mean, this guy here appearing more often. So in the next term, this would appear twice. So what I have here is this here, and maybe I have here the minus sign, so I put here the minus, and then I'm left with the sum from 0 to infinity of yt a to the minus 1 x to the k. For k equal to 0, it's just identity, so it's just this term here. For k equal to 1, it's just this term here. For k equal to 2, it will be the guy in the next term where I get this twice, because then I multiply again with this, and I have here again a yt a to the minus 1 x. And then I'm left with yta. So I'm always left with an x from the beginning and a yt a to the minus 1 from the end, but all the guys in the middle, they are multiplying always to powers of this guy. Okay. Yeah, and so you see essentially where I get this geometric series in this thing here. So this sum here, of course, this is now an ordinary geometric series for real numbers. So this is 1 divided by what I have here, 1 and okay, I have minus signs here, to minus 1 to the corresponding power, because I have here also alternating signs. Okay, and this means I have here again the plus, and I have y transpose a to the minus 1 x. Yeah, and so let's see, so what do we have? I have a to the minus 1 times the identity, that's the first term, that's a to the minus 1, and then the rest is a to the minus 1 multiplied with this guy here, x, y transpose, a to the minus 1, and then I'm dividing by this guy. That's exactly what I'm claiming there. Okay, so you see, this is just a very simple expansion of the geometric series, but in between we get terms which we can control, which are coming from the fact that x and y here are vectors. I mean, it's really important that I have here a rank 1 deformation, which is given by those vectors x and y, and then if I multiply them at many places, I will get inner products between y's and x's. Something. Good. Okay, and maybe I will also maybe go a little bit further with this. So actually, yeah, you see I have here some nice terms, which are just numbers, namely inner products, but this term here is of course not, this is a matrix, this is not so clear, but I can also bring this in a form like this. If I multiply this here now again also with y and x. So from this formula, we get something which we will really use in the following, namely I take a plus x yt inverse and multiply this now also with yt on one side and x on the other side, which is a number. I'm taking the inner product between this y and this vector. So I'm making a number out of it. And then I do the same on the other side. I have yt a to the minus 1 x minus, and then I have here yt x, I have the a to the minus 1 dx, the yt a to the minus 1, and at the end I multiply with x, and of course I divide it by this number. This of course doesn't change, yt a to the minus 1 x. Yeah, and now you see that I have now everywhere, I have the yt x, so I have exactly this quantity. I mean, that's the same quantity which I have here. But now I also have produced it here. I have yt a to the minus 1x, which is this number, and I have the same here. So now you see I have everything in terms of this number. And maybe we can even write this in a different way. So because what do I have? If I divide by this, I get the geometric series. But now I multiply it essentially with this. So I start a geometric series at the quadratic term. So if I call this x, I get the quadratic series in x, but starting at x squared. Here I have the linear term. So this means I have to, if I put this and this together, I get the quadratic series starting at x. So it's only the constant which is missing. So this here is the same as the geometric series, which starts at the linear term, which I can of course also write as 1 plus yt a to the minus 1 x, and then I multiply it with yt a to the minus 1 x. So this really gives just this geometric series which starts at this term. And of course one has to check that the alternating of the signs is not changed. So as you see, we get here a very, very nice expression for this inner product of the inverse of this perturbed thing in terms of the corresponding quantity of A. Good. Okay, and that's what we want to use in the following. So now we really should maybe go back to what we want to prove. So in the following, so we will choose, we will apply those things, of course, to our setting. And for the A, I'm going to take the sum of my Wishart matrix, but only summing up to n minus 1. So A is the sum of the xk transpose, where we are summing from 1 up to n minus 1. And then I also subtract the other terms which I also have there, namely n times set ip. Okay, so that's more or less that's my Cauchy transform as n, but I'm missing the last term here. And the last term I treat as a perturbation, which I put in this form. So now x and y are just the nth term here. So x and y in the above are just xn in this language. Okay, and then you see we can relate. This here is now where I'm summing up to n. This is really my Cauchy transform, the one which I want. But I'm trying to rewrite it in a form which gives me an equation in the end. And I get it in the form that I get essentially the Cauchy transform of a to the minus 1, or here. But then I have this term here. So the question is whether I can something say about this term. This is a to the minus 1, but taking inner products. And now the point is, this A contains only the vectors x up to n minus 1. And x and y are now the vector xn. And my vectors were independent. So the x1 up to xn minus 1 are independent from xn. So this means this A here is independent from those guys here. A, this means also a to the minus 1 is independent. And so this means that I can actually express this here in a nice form. I can really say what this is. As it is written there, it might not be so clear. Can I really do something with this? But essentially, we know by concentration, this here is more or less the same if I average over the situation. And if I average here, then I have here a guy A, which is independent from what I have here. And that's something which I can calculate. And maybe that's I also write in the next lemma. So I have here a matrix, and I have here vectors, and those vectors are independent from each other. And I take the expectation. And those vectors have a Gaussian distribution, because my vectors xn, they are Gaussian vectors. And for this, I really can calculate this here very nicely. And essentially, it will give me the trace So here we are really going to use the independence of my vectors xk. So in my Wishart matrix, I mean, a Wishart matrix is a quite complicated matrix, but the point is it is built out of those vectors xk, and they are independent. And the independence is now going to be used. I mean, up to now I haven't really used much of the structure. I have very general formulas, but they are not so explicit at the moment that I could use them without further concrete information. And the concrete information which I'm going to use is that I really can say more about this object here in our situation. Yeah, so maybe there's next lemma, one more lemma in this context. And then after this we really can try to put everything together. So here's the lemma. So let me take x. So the x is now, I mean, I'm taking now x and y to be the same. They will be xn. And so this means the x's are my Gaussian random vector. So x should be a Gaussian random vector in Rp with the identity matrix. That's the vectors which I consider here, where all the entries are independent and have the same distribution. A standard Gauss distribution. So x should be a standard Gaussian vector in Rp. And then I take a matrix, let me call it B. So it will be this a to the minus 1, but let me call it B. That it's the inverse is not important here. So let B be a P times P matrix, which is either deterministic or it can be random, but it should be independent from the x. I mean, in our situation, it is a random matrix. This here is a random matrix, but it depends only on guys which are independent from here. So it's independent from this. Okay, so I take this, either a deterministic or a random matrix. But in this case, of course, the random matrix should be independent from x. I mean, that's the main point. I mean, if I'm splitting my sum up to n in the sum up to n minus 1 plus the nth term, it's important that the next term is independent from what I had before. Otherwise, I couldn't go further. And so but that's the situation which I have here. And then I have that the expectation of what I have there, namely x transpose bx. So that's what I consider here. If y is the same as x and I call it a minus 1, I call this b. So then this expectation, and I'm taking the expectation over x. So if I also have some randomness here, I mean, I only average over the distribution of x, and then still I get something which depends on the randomness which I have here. Yeah, okay, but so this expectation, I'm claiming, yeah, what is this? Trace, yeah, so it's the trace actually. So it's the trace of B. So that's the statement here, and let us check this. I mean, this is again very easy, but again very important thing. Yeah, just write down what we have here. So I mean, the expectation of xt bx. So maybe let me write it also as an inner product. So I mean, this is the same as the inner product between x and bx. Okay, but now let me write down this in terms of the entries. I mean, x is a vector, so it has entries xi, and b is a matrix, so it has entries bij. So let me write this. I mean, I'm doing here matrix multiplication inner product, so of course I can express this very nicely in terms of the entries. So I have to sum over the indices I and j from 1 up to p. I take the expectation here. Okay, so now I have here xi, and I have to multiply it with bij xj. So I mean, if I'm summing here over j, this is b acting on x, and I get the I component of this, and then I take the inner product with x. This is this here. or maybe it's even easier in this form. It's just matrix multiplication of this vector with this matrix with this vector. I mean, I just identify the indices and I'm summing over all of them. Yeah, okay. But now, this expectation here is an expectation which applies to x. So I'm averaging over the distribution of x. And the Bij is either just a constant or it's a random thing which is independent of the x, which means I can take it out. So this here is just the Bij times the expectation of xi times xj. Yeah, but now, I mean, xi, this is my Gaussian random vector, where all the components are independent. So what is this expectation here? Exactly, it's just delta ij. It's either if I and j are different, it's 0, because then it's a product of the means, which are 0, and otherwise it's 1. We have normalized the thing to 1. So this is delta ij times 1. Yeah, okay, but then you see I have delta ij, so in my sum here I'm only summing over the I and j's which are equal. So this means yeah, this sum here is just the sum over I from 1 to p. So I mean this here is just then 1 in this case, and then I have here I is equal to j, I have just bii. So I'm just summing over bii from 1 up to p, but this is just the trace of this matrix. So this is the trace of b. So, okay, so you see very, very simple, very nice, but yeah, very important. So it really, I mean, we really can get, we can describe this in terms of matrix quantities again. Yeah, okay, now I think we are ready to try our hands at the proof of Marchenko-Pastur. We have all those bits and pieces, and we just have to use them and apply them and hope that now we really can change our Stieltjes transform for the matrices in such a form that we get an equation for them, at least asymptotically.